Here's another application of the class equation. Suppose G is a group of order P times Q, where P and Q are distinct primes. Show that G is abelian, or that the center of G is precisely the identity element. If we check our theorem against groups of low order, start with the permutation group on 3 letters. This has order 6, and we note that its center is the identity element, so this checks out. If we consider dihedral groups with 2 times P elements, where P is a prime greater than or equal to 3, these are going to be the symmetry groups for regular polygons with P sides. The center here is going to be precisely the identity element, and our theorem checks out again. Now, in this case, when we consider dihedral groups, if there's a center, it's going to be given by rotation by 180 degrees. That only occurs as a symmetry when our polygon has an even number of sides. So, if it's prime, we're not going to have anything in the center except the identity. Now, considering other products we could have, the next one up would be 15. In this case, there's only one isomorphism class, and then our group is abelian. So that's going to check out our theorem again. Now, for the proof, we just consider the center of our group. So the order of the center, that's a subgroup, so its order has to divide the order of the group. So it's either 1, P, Q, or P times Q. If it's P times Q, our group is abelian. So let's try to rule out cases P and Q. Now, since they're arbitrary primes, let's just suppose the order of our center is Q. Then we recall our class equation. So the class equation says, if I take the order of the group, that's equal to the order of our center plus the sum of the orders of conjugacy classes for elements that don't live in the center. Now, the rest is just arithmetic. We note, if I have any conjugacy class, its order is going to be given by taking the order of the group, dividing by the order of the centralizer of the element. Remember, the centralizer is just going to be the set of all elements in the group that commute with our element. Now, if our X is in the center, then we're going to have that the order of the conjugacy class is equal to 1 and vice versa. For all other X, well, let's think about the centralizer of X. All the elements that are in the center of the group live in the centralizer of X, but since our X is not in the center, it can't be the whole entire group. And here we're just considering possibilities of orders. So that's going to mean the centralizer of X has order Q, which means the order of the conjugacy class for X is equal to P. Now, let's consider each term in this equation. So we're going to have P times Q equals Q plus a sum of a bunch of P's. So that means PQ equals Q plus K times P, or K times P equals P minus 1 times Q. P can't divide P minus 1. Since P and Q are distinct primes, P can't divide Q, and that means we have a contradiction. So we rule out P and Q as possibilities for the center, so we're either abelian or order of the center is equal to 1. In that case, it's precisely the identity element. Now, if we don't have access to the class equation, not a problem. We could show our result using elementary methods. First, let's assume the result. If G mod the center of G is cyclic, then G is abelian. We'll show this after the proof. Now, if the order of the center of G is equal to Q, then the order of the quotient group G mod the center of G is equal to the order of G divided by the order of the center, which is equal to P. Since P is a prime number, the order of the quotient group is a cyclic group of order P, and we invoke our first result. So that means that G is abelian, but then G is equal to the center of G, which means the order of the center of G is equal to P times Q, and that contradicts our assumption. So that's our result. Now, for the first result, let's assume that G mod center of G is cyclic. So that means there's going to be a generator for the quotient group. So that says there's going to be an x in our G such that the coset x times the center of G, which we'll call x bar, generates our quotient group. Now that says a few things. First, it says that I can write G mod ZG as a group as, okay, we have identity element, then x bar squared, all the way up through x bar to the n minus 1. That's all of our group elements. Now, as a set, this says that G is equal to the center of G, union x times the center of G, all the way up through x to the n minus 1 times the center of G. This is going to be a partition. Now, that says we can write every element of G in the form x to the k times z, where z is going to be an element in the center of G. Now, we check the Abelian property. So I'll take any two elements in our group. Okay, I can write them as x to the k, z1, times x to the l, z2. And we note the x's commute with each other. The z's are in the center, so they commute with everything. So we can just rearrange all the terms to see that our G is abelian.